So thus far we've talked about Lewis structures. You guys learn how to draw them using your VSEPR model. And so the next step is to actually see how these molecules would exist in the real world. And they exist as 3D models. So we're going to be talking about the molecular geometries that they assume. Now, just as a quick note, some of this is going to be review from first year, some of this is going to be new. All of the molecular geometries that I share with you here, those need to be memorized before we begin school, so on the first day of school. All right, so really quickly, when we're deciding what the molecular geometry of a molecule is, the first thing we need to determine is the electron domain geometry. So the electron domain geometry is simply adding, it takes into account both the bonding domain and the non-bonding domain. So what those means, your bonding domains is simply the number of covalent bonds that your molecule has, while your non-bonding domains are simply the number of lone pairs of electrons. All right, so let's look at something that's familiar. If you look here, if you have a total of 2 bonding domains, if you have a total of 2 electron domains, okay, if you look here, if you have 2 that are bonding and none that are non-bonding, then your molecular geometry is going to be linear, all right? And the bond angle for this molecule will be 180 degrees, okay? If you have an electron domain geometry that has 3 total, then the electron domain geometry is going to be trigonal planar. Now, there are 2 different options for molecular geometries. If you have 3 bonding domains and 0 non-bonding domains, then the molecular geometry will be trigonal planar. And in that case, the bond angle will be 120 degrees. If instead you have 2 bonding and 1 non-bonding, as you can see for that bent shape right there, that is your molecular geometry bent. And since that lone pair is actually going to force the other 2 atoms further downwards, the bond angle, while it's close to 120, it's actually going to be less than 120. So a good example of this is NO2. So as you notice, it's got 2 bonding domains there because keep in mind a double bond counts as 1 bonding domain, okay? And then it has a lone pair of electrons on top. If you have 4 electron domains, your electron domain geometry is tetrahedral. So there are 3 different options here that we care about. The first one is if you have 4 bonding domains and 0 non-bonding domains. In that case, the molecular geometry is going to be tetrahedral, okay? And the bond angle is going to be 109. If instead you have 3 bonding and 1 non-bonding, as you can see for the next option, your molecular geometry or your molecular shape is going to be trigonal pyramidal, okay? Because you have that lone pair of electrons again, instead of being 109, your bond angle is going to be a little bit less than 109. And finally, if you have 2 bonding and 2 non-bonding, then your shape is going to be bent, and the bond angle is going to be less than 109 again. Now, note, if I ever ask you, if the AP test ever asks you what's the molecular geometry, we never put the electron domain geometry. We always put the molecular geometry. The only value in knowing the electron domain geometry is, for example, if I know that I have a bent molecule, right, with water, for example, then because I know that it's tetrahedral for the electron domain geometry, that then tells me, hey, your bond angle is going to be less than 109, since for a tetrahedral, the bond angle is 109. But we never put tetrahedral, because technically it's not, it's bent. The only value of the electron domain geometry is to help you determine the bond angle. So this here is the new material. So these are called expanded octets. So instead of having 2, 3, or 4 electron domains, we suddenly have 5 electron domains. Okay, so if you look at this, for example, for PCl5, you got 5 atoms coming off of your central atom instead of just 4. The other way that you know that you have an expanded octet, if you look, for example, at XeF2 right there, okay, so it's right in the middle right there. If I count the total number of valence electrons that molecule has, it has 22. So if I were to fill in this Lewis structure and made everyone content, right, with those 8 valence electrons, I would only be using 20 electrons, but I need to use 22. So you add an extra pair of electrons. If you ever have more than what you need, you're going to add those extra electrons to the central atom, and that will create an expanded octet, as you can see for XeF2. So I'm going to go through and explain all of these shapes, and then you're going to get some practice drawing out the Lewis structures and then predicting the molecular geometry. So if you have a total of 5 bonding domains and 0 non-bonding domains, then your molecular geometry is trigonal pyramidal. Okay? If you have 4 bonding domains and 1 non-bonding domain, you have what's called seesaw. So you can imagine 2 of those, the 2 bent atoms right there are kind of like what would position it on the ground, and then the seesaw is what goes back and forth. If you have 3 bonding and 2 non-bonding, it's T-shape. 2 bonding, 3 non-bonding, it is linear. So all of those have 5 electron domains, and therefore we call it trigonal bipyramidal. You do not need to memorize the angle for it. If you actually look at it, it is kind of obvious. It's 180 from the top to bottom one, if you're looking at the trigonal bipyramidal shape, and then you can see it making a right angle. But I haven't recently seen a question asking about bond angle, and definitely not for seesaw, T-shape, or linear. So yeah, the bond angle is 180 and 90, but beyond the scope of the class, honestly. Okay. If you look at the octahedral electron domain geometry, okay, we've got 3 different options here. So if I have 6 bonding and 0 non-bonding, the shape is octahedral. If I have 5 bonding and 1 non-bonding, the shape is square pyramidal, because you can see a square at the bottom, and then that 1 atom up top makes it into a pyramid. And then finally, if you have 4 bonding and 2 non-bonding, then it is square planar. Okay? So these are all your expanded octet molecular geometries. It's a matter of memorizing them and then being able to draw them with the Lewis structure and then identify what the molecular geometry is. So make sure to do the practice so that you can get some practice with it, and then you will need to memorize those shapes. All right, so I'm going to show you 2 different examples of an expanded octet and determining the electron domain geometry and the molecular geometry. So here I've got sulfur hexabromide. So the first thing I need to do is determine the number of valence electrons that it has. Well, sulfur has 6 valence electrons. Bromine has 7, so it's going to be 6 plus the 7 electrons times 6, because there are 6 bromines. So that is going to be a total of 48 valence electrons. Okay? Now I'm going to draw this. So keep in mind, I'm going to have sulfur as my central atom. I'm going to have 6 bromines coming off of it. So I automatically know this is going to be an expanded octet simply because I already have 6 bromines. Okay, remember everyone wants 8 valence electrons, so bromine I'm going to add 6 to each bromine so it can have a total of 8. Okay, and when I count my total number of valence electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 46, 44, 46, 48. I'm using 48 valence electrons. So this is my structure. Now, keep in mind that when I'm determining my number of electron domains, because all of these are bonding, I don't have to add anything together. I just know that my total number of electron domains is going to be 6. My electron domain geometry, because I have 6 electron domains total, is going to be octahedral. And then my molecular geometry, keep in mind, since I don't have any lone pairs of electrons on sulfur, my electron domain geometry and my molecular geometry are going to be the same. Okay? Now, really quickly, just as a side note, notice that this drawing is not perfect. I'm not taking into account the fact that I have some bromines that actually, if they were following the VSEPR model, would be coming out of the board, some would be going into the board. I don't take that into account simply because I'm artistically challenged. So, when we are using an expanded octet, I am not going to expect you to follow the VSEPR model like I did for non-expanded octet examples, right? So when I gave you tetrahedral, I asked you to draw it, for example, like this, right? Showing that the elements are avoiding one another as much as possible, right? Because their electrons repel each other. I don't expect that for expanded octet simply because I don't expect you to be able to draw it like that. Okay? All right, let's look at the second example, XeCl4. Okay. So the first thing, again, that I need to do is I need to count my total number of valence electrons. Xenon has 8, chlorine has 7 times 4, which gives me a total of 36. So xenon's going to be my central atom. I have 4 chlorines coming off of it. Right now, xenon is happy with 8. Cool. I'm going to add 6 to each chlorine. And if I added up the total number of electrons I'm currently using, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, I'm using 32 electrons. So that creates a problem because I should be using 36. This is a new problem. Normally what happens is I have, for example, 32 electrons that I'm allowed to use, but I'm using 36. I'm using too many. And so when I use more than I have, that's when we use a double or a triple bond. That's not the case here. I'm actually supposed to use more than what I'm using. And so that tells me I'm going to have an expanded octet. And where I put those extra 4 electrons, I'm actually going to put them on my central atom. So xenon now has a total of 12 electrons on it. And I'm going to talk to you about how we know what elements can do that and which ones cannot in a second. So my total number of electron domains, I've got 1, 2, 3, 4, 5, 6 total electron domains, which means my electron domain geometry is going to be octahedral. Now here's where this differs from the previous problem. I've got 4 bonding domains and I've got 2 non-bonding domains, which means my molecular geometry is going to be square planar. So you memorized last year the molecular geometries for non-expanded octets, for example, tetrahedral, trigonal pyramidal, trigonal planar, etc. You now need to go right now and memorize these expanded octet problems because we're not going to have time during the school year for you to memorize them. So use the summer, memorize these, say, okay, if I have 4 bonding domains and 2 non-bonding, what shape would that be? If I have 5 bonding domains and 1 non-bonding, what shape would that be? Okay, and what we're concerned about again is the molecular geometry, not so much the electron domain geometry. But the electron domain geometry might actually help you to remember the molecular geometries. All right, so I hinted at this just a minute ago, talking about, okay, what elements can form an expanded octet and which ones cannot. Okay? Notice here in your first and second principal energy levels, they do not have access to the D sublevel. The D sublevel starts in the third principal energy level. So if you're in the first or second energy level, like for example, nitrogen or oxygen or carbon or fluorine, those elements cannot form an expanded octet. They just don't have access to enough electrons or they can't form enough orbitals. Instead, in order to form an expanded octet, an element must, the central atom must be in the third energy level or lower. So starting in this third energy level, sulfur, phosphor, for example, they can form an expanded octet, just like what we saw within our example of sulfur hexafluoride, right? So if a question asks, can this element serve as a central atom in an expanded octet? If it's not in the third energy level or below, it cannot because it does not have access to the D sublevel.